See how the equations of kinematics are derived, we're going to do some experiments or do some analysis on a graphical representation of accelerated motion. The first equation we can look at is the definition of acceleration itself. Now, the definition of acceleration is the rate of change of velocity, or the change in velocity over the change in time. So our change in velocity is our final minus initial, and our change in time there, delta t, that's our elapsed time. That's pretty much the definition of acceleration, so we don't need to derive that. But in order to derive some of the other equations, we can look over here at our velocity time graph. So we have a velocity time graph, and we have a diagonal line with a positive slope, which indicates positive uniform acceleration. So we have here our initial velocity, vi, our final velocity, vf, and we know from uniform motion that the area under a velocity time graph, so this area in here, gives us our displacement. So the total area down here is going to be our displacement. So how do we calculate that area? The first way we can calculate the area is by simply dividing this into a rectangle and a triangle. The area of the rectangle is going to be delta t across the bottom, and then the height here is vi. So the area of this rectangle is vi delta t. The area of the triangle is going to be half of vf minus vi, because that's what this represents here, is the difference between vf and vi times delta t, which is again across here. Now that's kind of awkward, but if we look up here, we can see that vf minus vi is a term in our acceleration equation. So if we substitute in here, rearranging this equation, we see that vf minus vi is actually equal to a delta t. So we can substitute a delta t in here, and this term becomes 1/2 a delta t squared. So from that we can see that our total displacement, the total area of that space, can be given by displacement, delta d, is equal to vi delta t plus, so that's the area of the rectangle, plus the area of the triangle, plus 1/2 a delta t squared. And that is one of our formulas. We have two of our equations, but those are not the only ones that we can figure out from this. So I'm going to just erase this and erase this just to clear some space. And what we're going to do is we're going to do basically the same thing, vi delta t, but now instead of looking at that triangle, that shape, what we're going to do is we're going to use a big rectangle, and we're going to subtract this triangle. Okay, so we have, again, we're going to find the area in here by finding the area of this big rectangle and subtracting the area of this triangle from it. So the area of the big rectangle is in fact not vi delta t. The big rectangle is vf by delta t. So that's vf delta t. The area of this triangle, however, is exactly the same as the area of this triangle, which is 1/2 a delta t squared. But now we're going to subtract it to leave us with this, rather than adding it as we did previously. So in this case, our delta d is equal to our final velocity times time minus 1/2 a delta t squared. So now we have three of our equations. The third way we can find the displacement is not by adding rectangles and triangles, but by using the trapezoid formula. So let me just clean this up a little bit. And what we're going to do is we have a trapezoid with two uneven sides, and the area of a trapezoid is equal to the average of the uneven sides, which is in this case VI plus VF over 2 times the width. So that's times delta t. So our displacement, which is, as we recall, and we've repeated several times, is this area in here, is equal to the average velocity, VI plus VF over 2, times delta t. To review, we have this formula, which has no acceleration term. We have the ones we've previously calculated. We have our delta d is equal to VI delta t plus 1/2 a delta t squared, which has no final velocity term in it. We have delta d is equal to VF delta t minus 1/2 a delta t squared, which has no initial velocity term in it. And we had our definition. Our acceleration is equal to VF minus VI over delta t, which has no displacement in it. But you'll notice that time is in all of these. So we want to have one more equation where we get rid of time. When we want to get rid of a variable, one of the best ways to do that is to merge two equations and use substitution. So actually what we're going to do is we're going to merge these two equations. So I'm going to scroll down to get a little bit out of the way. I'm going to rewrite this equation in terms of time. Delta t is equal to VF minus VI, go away, over A. I almost said delta t, over A. And now we're going to insert that value into replacing that value of delta t. So that becomes delta d, our displacement, is equal to VI plus VF over 2 times VF minus VI over A. And I'm just going to make a slight change here to make it a little easier. It's very subtle. Ready? VF plus VI over 2 times VF minus VI over A. And if we remember, anytime we have an addition and a subtraction multiplied together, we get our difference of squares. So our delta D is equal to VF squared minus VI squared over 2A. And usually we rearrange this equation by moving everything onto the other side except for VF, and we wind up with VF squared is equal to VI squared plus 2A delta D. And that is our fifth and final equation.